Welcome back to Unit 6. Last week we talked about using the equation of a derivative or a rate function to find the equation of the original quantity. We did that using slope fields, which basically gave us a sense for what that original function should look like. And we also did this by solving differential equations. In fact, we talked about how there's two kinds of solutions to a differential equation: a particular solution that goes through a point that you're given, and a general solution which has a plus c at the end. Today we're going to start talking about some more sophisticated methods for finding an antiderivative, because the truth is there are a lot of equations that you look at and you may not immediately see the antiderivative. In particular, today's strategy is using U substitution. In class today we talked about indefinite integrals and the difference between an indefinite integral, which is this one, and a definite integral that has what are called limits of integration, like 0 and 2. Remind me again, what's the difference between these two? Exactly, a definite integral's answer is just a number that represents the area under the curve, whereas an indefinite integral, which doesn't have those numbers in front, represents a family of functions. The most important thing that I mentioned in class was to point out that this differential dx is part of the integral symbol, and you can't write an integral unless you also have a differential. We talked some more in class about what that differential means and the difference between, for example, a dx and a du. We noticed that you can only evaluate an indefinite integral if the variable inside your equation matches the variable of integration, which is the variable from your differential. We evaluated each of these three examples and we saw that they turned out to be different. I'll just scroll through it here for anybody who missed class. Assuming that x is x cubed plus 1 and u is x squared, we can evaluate the first integral as follows. The second integral would look like this. And the third integral would look like this. And of course, you've noticed probably that these do in fact all equal different function families, not just different functions. And that was an explanation for why that differential matters, why the variable of integration must match the variable inside the function before we can actually go ahead and find the antiderivative. From there, in class, we went on to talk about evaluating integrals using U substitution. The first example was sine x e to the cosine x dx. In this example, we chose to substitute u as a new variable for the expression cosine of x. Doing that meant that du, or negative du, was the same thing as sine x dx, and so we were able to transform our integral that had a variable x into a much simpler integral using the variable u. Once we took the antiderivative of this simpler integral, we substituted back in so that our final answer was in x. We used a similar process for b. In fact, try working it out yourself. See if you can remember what we did in class to evaluate b. Great, hopefully that was easy. If it wasn't, it's just an indication that you should review your notes a little bit before moving on. Here's what the work looked like. Notice that I'm strategically choosing u to be the expression that is kind of in the most complicated position. Here I decided the most complicated position was to be inside of the radical symbol. Everything else follows, and of course don't forget plus c and to convert back to your x variable. Remind me again, what did we do for c? Right, exactly. The first step we took for c was to convert the whole integral with cotangent into the expression cosine over sine. And that was like kind of a creative step we had to take. It's something we didn't necessarily know was going to work. We tried it because we could, and it turned out to really be helpful. From there, we chose sine to be u, because I know the derivative of sine is cosine, and sine on the bottom of this fraction is in the more complicated position. Okay, here's what's next. So now that you are adept at using U substitution and recognizing what U should be, there are a couple integrals that require substitutions of another kind, and that's a trig identity. Sometimes we'll use U substitution in addition to a trig identity. I want to kind of break this down into three simple situations, but in the back of your mind you should know that ultimately the key to success is being flexible, trying things, and when they don't work out, trying something different. Before I talk about tip 1, I actually want to suggest a tip 0. And the tip 0 is that all of these will be much easier to do if you really know your trig derivatives. So what do you do if you don't really know them? Well, I would take another tab open in your computer right now, or if you have it in your notes, go ahead and Google trig derivatives. Even if you know them really well, sometimes you can spark your memory just by looking at a chart. This is what I get when I Google them, and I can come up with a nice little list of trig derivatives. Having this right in front of you will be very helpful in finding the actual antiderivatives. The other thing, which you aren't going to need for the first example but could be really helpful, is to have a list of trig identities. Again, I would say go to Google. First hit you get is going to give you a huge long list of identities. As you get better with this, you'll start to have an instinct for which identities you're going to want to use. But instead of agonizing over, do I have the right one, do I have the wrong one, take a look, use the resources that you have. Okay, so here's what tip 1 actually says. It says use identities to reveal known derivatives. If you think about it, when we evaluate this integral, I want to try and see a derivative inside the integral so that I can write its antiderivative for my answer. The identity I'm going to use for this one is a very simple identity that has to do with cosine. Can you see what it should be? So I'm actually going to use the fact that 1 over cosine equals secant. Now, seeing the cosine squared, your instinct might have been to use the Pythagorean identity, that cosine squared equals 1 minus sine squared, and it's good that you recognize that. Here's why, though. I'm thinking ahead about what I want to see, and I happen to know that secant squared is the derivative of tangent. And so when I see 1 over cosine, which I do right here, and then it's squared, I actually recognize that that's going to be the same thing as secant squared. And the great news about the integral of secant squared is that that's just a very easy antiderivative to take because I know that the derivative of tangent is secant squared. Now, just in case some of you are feeling some little anxiety butterflies because you chose the wrong identity, let's take a look at what would have happened. So first of all, instead of calling it the wrong identity, let's call it the less helpful identity. Because it's not that you're really making a wrong step, it's just that it turns out to not help. And it's really important that you start to trust that you will see why something is or isn't helpful, and you'll be able to come up with a different idea if it's not. In this case, it's actually perfectly fine to replace cosine squared with 1 minus sine squared. This is a true mathematical statement. You haven't made an error. But look at this integral. When you look at this integral that we get by using the identity, is this an integral that's distinctly easier for us to solve? Do you see a known trig identity here? No, you don't. So this is why using the secant identity was helpful, and the cosine squared Pythagorean identity is not helpful because it doesn't simplify the integral. With time, you're going to start to be able to look at this integral and imagine in your head these two options and pick this one. When I made this choice, it wasn't that I looked at this and instantly knew that this was the better identity. It was because in my head, I imagined my two options, and in my head, I saw that this option was more helpful. Okay, tip number 2. Tip number 2 says split up odd powers of sine or cosine to use the chain rule. Notice the 3 right here. Sine cubed of x means that sine of x is being cubed. It's an odd power. This trick that I'm going to show you only works if you have odd powers specifically. When you first see this integral, sine cubed, your instinct might be that we should choose u to be sine. And that makes some sense because then this integral would just end up being the integral of u cubed, and that's a pretty easy integral. But there's a problem. And the problem is that if u is sine, then du is cosine. And there has to be a cosine somewhere in the original integral that we can replace with the du. But since we don't see a cosine, we actually can't use this substitution. So instead of using the substitution, we're going to split sine cubed up into sine squared times sine. And I realize it's not immediately obvious why that's somehow simpler. So trust me for a moment, and then you'll start to see how this is going to work. Notice that more generally, any odd power of sine or cosine could be split up in the same way so that the first expression was an even power, and the second expression was just a single sine or cosine if we were doing cosines. The next thing we're going to do is we're going to use a trig identity. Specifically, we're going to use the Pythagorean identity to replace sine squared with 1 minus cosine squared. And the reason that this is helpful is because we now have an integral with both sine and cosine, which means we're in a great position to do u substitution because I see those two functions, the function and its derivative. Which one do you think should be u in this case? That's right, you want u to be cosine because cosine's in the more complicated position, whereas sine is just ready to be substituted with the dx. Now notice that du actually equals negative sine of x dx, so if we substitute for sine of x dx, we actually want to substitute negative du. And the next line would look like 1 minus u squared times negative du. And that's a very easy antiderivative to find. Don't forget the negative is just a coefficient out front, and of course, don't forget your plus c. And then last step, substitute back in to get rid of the u variable, which is really something we just made up. And we end up with a final integral of negative cosine of x minus cosine cubed over 3 plus c. Of course, you could also put just 1 over 3 if you wanted to. Since tip number 2 only works for odd powers, you can try tip number 3 if you have an even power. This is going to require two identities, which are a little bit more esoteric. So to be perfectly honest, when I first started preparing for this lesson, I had to look them up. I Googled trig identities, and the identities you're going to want to remember are these two right here. You might hear them referred to as power reducing, and that's because these identities allow you to go from a sine or a cosine squared to an expression that has a sine or a cosine, actually specifically a cosine, that is not being squared. This is a variant on the double angle formula. It can be derived from the double angle formula if you have that memorized, or you can just take a moment to memorize these two. Here's how you can use it. So let's say I'm starting with cosine to the fourth. First thing you want to do is rewrite that so that you have cosine squared. In this case, it's easy enough to say cosine squared to the second power is the same thing as cosine to the fourth. Once you have cosine squared, you're going to replace that expression using the trig identity I just showed you, the one for cosine. So this expression right here is what we're going to use, and we're going to make that replacement. It would look like this. Notice that when I write a trig identity, when I use it, I'm quoting the trig identity here. I want you to do that on your problem sets and practice problems so that other people can identify how you are solving your problem, and in case you use the wrong identity, easily identify where your error is. So here's where it gets a little hairy. This is already a better expression because we've gone from having something to the fourth power to just something squared. But we are going to actually need to square this out, and we're going to use an identity one more time. Notice that when you square the bottom, 2 squared on the bottom just becomes 1/4, and that's a coefficient. I'm in fact going to pull that out so that I can kind of ignore that and keep simplifying the inside. So the rest of this requires a couple algebraic steps that take a little while, and I want to make sure you have time to practice. Basically, after we applied the trig identity, I FOILed, I applied the trig identity again, and then I took an antiderivative, and you can double check that the derivative of each of these expressions on this line equal the derivative inside the integral symbol. And then I just simplified. You won't have any examples this hard until we get to the problem set on Wednesday and Thursday, so let's just practice some of the basics here. These are the ones for you to try. Go ahead and pause the video. When you press play, I'll show you the answers in the work. Here's the work for number 1. Press pause if you need more time to look at it. Here's the work for number 2. Again, press pause if you need more time to look at it. Here's the work for number 3. Press pause if you need more time to look at it. Number 4 and 5. That'll be it for tonight.